Guys, welcome back to our virtual learning. So this is lesson 3. Lesson 3, we're going to talk about graphing the last two types of trig functions, which are tangent and cotangent functions. Let's go ahead and jump into that. Okay, let's go ahead and graph the tangent graph really quick here. So, at negative, I'm going to start in a kind of a strange place. Notice I'm going to start with negative pi over 2. Now, in case you guys forgot, up here is positive pi over 2, right? And that's because that's whenever you're going in a clockwise, or sorry, counterclockwise fashion. But negative pi over 2 would be down here. So negative pi over 2 is coterminal with 3 pi over 2. So we're actually going to be starting there. Now, you have to have out your tangent unit circles. If you don't remember what the tangent values are at these points, it's a lot easier if you just have that out. It's undefined. So at that point, tangent is undefined. There is no solution. The next one I want to do is negative pi over 4, which is here. This is pi over 4 if you're going in the positive direction, but in the negative direction, that's the negative pi over 4. At that point, tangent, if you're looking at your tangent circle, is 1. At 0, tangent is 0. At pi over 4, sorry, I made a mistake. This was negative 1, by the way. I made a boo-boo there. At pi over 4, that's the positive 1. And at pi over 2, it's undefined again. Okay. So let's go ahead and graph this really quick. So I'm going to put two negative values over here. Negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. Okay. So at negative pi over 2, it doesn't exist. Now the reason why it doesn't exist is because at that point, the graph can never reach that value. So it's actually got a vertical asymptote there. At negative pi over 4, we reach a negative 1 value. At 0, we're at 0. At pi over 4, we're at 1. Looks like a straight line, but it actually won't be. You'll see in a minute. And the last one, pi over 2, is also another vertical asymptote. So now, here's how this works. This graph is going to be approaching that asymptote on that side and approaching the asymptote in the downward direction on this side. And so it's actually got a little bit of a curve to it. It's not really a straight line. Matter of fact, a better way to connect those two middle dots might be like maybe something like, I'm not doing it very good. These are pretty hard to draw, but it's got like a nice little curve there in the middle. But that's what a tangent wave looks like. Okay, and since it's periodic, once again, you would have just a repetition of this on the other side looking like that, and another one over here. It just kind of keeps going on and on forever. Okay, cotangent looks quite similar, but I'm going to use a different set of angles to demonstrate that. We're going to start with 0. Now, cotangent, if you want to find what cotangent of 0 is, what you need to do is find the tangent of 0 and do the reciprocal of it. So the tangent of 0 is 0, but there is no reciprocal of 0 for cotangent, so that one's undefined. Tangent of pi over 4 is 1, and the reciprocal of that will be 1. Tangent of pi over 2 is undefined, and the reciprocal of that will come out to be 0, and so on. It's actually going to look very much the same with a slight difference. The shape will be identical. So my angles are 0, pi over 4, pi over 2, 3 pi over 4, and then pi. Okay, so we have a vertical asymptote at 0 because that's undefined for cotangent. At pi over 4, it's up 1. At pi over 2, it's at 0. At 3 pi over 4, we're at a, might have, oh, this one was negative actually. That was my move. At 3 pi over 4, it's at negative 1. and then at pi we have another asymptote. So it's almost the same shape, but it's backwards, right? And it's also starting in a different place. Remember, tangent was half on the left, half on the right of 0. This one's all the way to the right of 0, and it's going backwards. You're using a completely different set of angles, and it's going down instead of up as we move left to right. Okay? But like tangent, though, it just repeats on the either side of it, so there it is. So that's tangent and cotangent. That's what they look like. Here's a much prettier graph. So you can see how they're the same. They pretty much have identical types of shapes, but you can see also that they're opposite directions of each other. And the other thing I want you to pay attention to is the angle differences. Notice that tangent starts at negative pi over 2 and ends at pi over 2, whereas cotangent starts at 0 and ends at pi. But something that their angles do have in common is that they go up by intervals of pi over 4. Like if you were to add pi over 4 to this, you get that. If you add pi over 4 to that, you get that. If you add pi over 4, you get that. If you add pi over 4, you get that. So they're going up by intervals of pi over 4. Same thing over here. So they have the same intervals, but different directions and different angles overall. Okay. So let's talk about transforming these graphs a little bit. So what this thing is going to do is this is going to stretch the graph, and this is going to shift the graph up. Okay, so let's back up a little bit and talk about this on the tangent real quick. So right now, notice that the intersection point is always at the origin. But if we were to shift the graph up, let's say this was a 2, right? That means every point gets shifted up 2 spaces. So that means that this point here would go up 2 spaces. This one here would also go up 2 spaces. And this one would go up 2 spaces. So the whole graph would look like this. That was terrible. I'll draw that again. All completely look like this. Okay, so the whole graph gets pushed up 2 spaces. So here's what I want you guys to think of from now on. That k, that plus k value right here, that plus k, basically what that's going to tell you is how high your middle point is to start at. Usually it's at 0, but if whatever k is, that's where you'll start. So if k is 2, then you start at 2. If k is negative 2, then you start at negative 2. What's another feature that we need to look at? Let's take a look at the stretch factor. Now the stretch factor here, that's going to take your graph, which may usually look like this, right? And it will either compress it so it looks flatter, or it will stretch it so it looks longer. Okay. Now, basically, what this thing is going to do is like, let's say it was 2. Again, I'm just going to use 2 because the graphs I have don't go very far. So let's say this is 2. And let's say that k isn't there. Let's just say k is still 0. Okay. So if I do that, I go back to my tangent graph, I'm stretching it, but I'm not shifting it. So my middle point is still going to be here. But since I'm stretching it, now instead of going over 1 up 1, it's being stretched by 2, so now it's over 1 up 2. So this point goes higher, and this other point down here goes lower. So the graph will look more like this now. It gets stretched a lot. Let's say, on the other hand, that I made this number here a fraction instead. Like let's say I made a half instead of 2. Okay, what would that do? Well, that would mean that when I go over, instead of going up 1, I only go up halfway. And this way I go over 1, I only go down halfway. And so it would look more like a little bit more flat. Okay, so basically what this number does here is it stretches or compresses the function, and what it basically does is it tells you just how far away this dot stretches away from this middle dot. Same thing here, just in the opposite direction. Now the same transformations apply to cotangent. Okay, the K is that middle point, just how high up is your middle point. So once again, shifting back here to our tangent graph, it starts on the x-axis at 0 once again, for the y value anyway. The x value is pi over 2, the y value is 0. But if you have a plus k, it'll shift it up or down depending on whatever that k value is. And in the same way, the a number in the front will stretch these other two dots, one on the left and right, farther away from your middle point. Okay, but what you have to remember is the directions to go in. So for tangent, it's right and up, left and down. Whereas for cotangent, it's left and up, right and down, because it's going in a downward direction. Okay, so that's transformations of tangent and cotangent. So if I were to write some notes here, I would say that this is your height of your middle point. I guess you could call it the midpoint if you wanted to. That'd be easier, right? And this one is your stretch factor. Okay, and so what I would do is I'd maybe write a little note over here for tangent and cotangent about what that looks like. For tangent, it's to the right 1 and up, actually I should say right pi over 4, and up a. And then it's left pi over 4, down a. Whereas with cotangent, it's left pi over 4, up a, and right pi over 4, down a. That way you get those different directions. But either way, the height is what I'm focusing on here. It's down or up a in either direction. So that's what the a tells us. All right, so let's go ahead and give you a summary here then of what we just talked about. So set your graph up with one of the following sets of angles. If you're working with tangent, we're going to do the angles I gave you guys earlier were negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. But if you wanted to do them in degrees, it would be these, right? Pi over 2 is the same as 90, pi over 4 is the same as 45, right? So you could set your graph up with degrees or radians either way. Now for cotangent, the angles I gave you guys were 0, pi over 4, pi over 2, 3 pi over 4, and pi. But in degrees, that would be these things. Pi is 180, 3 pi over 4 is 135 degrees, pi over 2 is 90, etc. Okay, so set your graph up with one of these sets of angles. If you're doing tangent, it's this set or this set. If you're doing cotangent, it's this set or this set. So the next thing we're going to do is we're going to sketch our asymptotes, the vertical asymptotes at the first and last theta values. First and fifth or last theta values. Then you're going to plot your midpoint. So we're going to find at this middle angle here, we're going to go up k or down k, if it's positive or negative, at the middle. That'll tell us the height of our midpoint. And then we're going to plot the other 2 points using our stretch factor. So from k, we'll go over and up a, over and down a. And the direction depends on whether we're working with tangent or cotangent. Okay. So let's go ahead and try to bring these steps to life a little bit. We're going to graph 2 tangent theta minus 1. 2 tangent theta minus 1. So I'd encourage you guys to take a look at the step that we had on the last slide there as we go along. The first step is to set up your graph with the appropriate angles. Now, since this is tangent, we're going to have 2 spaces on this side, 2 spaces on this side. Okay. Now, if you want to use degrees, I'll use degrees this time. The degrees would be negative 90, negative 45, 0, 45, and 90. So that's step 1. Step 2 is to put in the vertical asymptotes at the first angle and at the 5th or last angle. Step 3 is to plot K at the middle angle. Plot the K value at the middle angle. So this is my K value, and this is my middle angle. Okay, so at that middle angle, I'm going to go down 1 and put a dot. So that's plotting K. All right, my third step is to use the vertical stretch factor. Now, since this is tangent, remember, tangent is going to go in this direction. That's what tangent looks like. So that means if I go to the right, I'm going to go up. Right is up, left is down, right? So I'm going to go left over to the 45 degrees and then up 2 spaces. So left to 45, up 2 goes here at the 1, and then left 40 to the 45 and down 2 puts me at negative 3. So we end up with something that looks a little bit like that. I like to connect these first, give them a little bit of a curve like that, and then stretch the asymptotes after that. Once you have one done, just kind of go ahead and roughly sketch some other ones to the left and right that kind of mirror that, and you're good to go. Okay. So that's one example. Let's do another one. So on this one, we're going to graph y equals 1/2 cotangent theta. Y equals 1/2 cotangent theta. Okay, so step 1 is to set up your x-axis. Now this time I'll use radians instead of degrees just to kind of show you can do it either way. If you're using radians, we start at 0. The next, and we're going up by pi over 4 every time. Following. So that's step 1. Step 2 is to put in your vertical asymptotes at the first angle and at the last angle. Step 3 is to plot your K value, which isn't there, which means that it's 0. So I'm going to have a height of 0 at the middle angle, pi over 2. So it's right on the x-axis, like it usually would be otherwise. And then after that, we're going to use our stretch factor. So now remembering that cotangent goes this way, which means that if I go left, I go up, and if I go right, I go down. So I'm going to go right 1 space, and down 1/2. And left 1 space and up 1/2. And there's my 3 dots. And I'm going to give them a connection here. That one a little bit of bend that way, a concave up bend. This one a little bit of a concave bend down that way. And then from there I'll just stretch them towards the asymptotes. And then we're going to copy that shape to the left and right. Okay? And there's our cotangent graph. So at this point I'll let you guys try these 2 problems. Take a moment and see if you can get those right. Pause the video here, graph them, and when you unpause the video, you'll see the solutions for each one. Okay, so here are the solutions. On this one, I chose to use radians for the tangent, and on this one, I chose to use degrees for the cotangent. It doesn't matter what you chose, degrees or radians. I'm just kind of switching it up so we get used to it. What does matter is that for the first one over here, you had your midpoint at 0, -1. And it matters that you went over to the right to pi over 4 and up to +2, left to the -pi/4 and down to -3. For the cotangent one, you should have had your midpoint at 90 degrees and down 1. The middle angle is 90 and the k value is -1, so we're going down 1. And then since cotangent goes in this direction, we're going to go left to the 45 and up a half, right to the 135 and down a half, and then we're going to connect our dots in that fashion. And I understand that drawing these lines can be a little bit hard, so I'll kind of show you guys how I do it. I think of concavity. So basically, if I want to connect this point to this point, I know it's got to be concave up, so I'm going to give it a little bit of an upward bend. And then I'm going to connect the other point, but with an opposite bend, a downward bend. And then after that, I just kind of try to smoothly stretch the line towards the asymptote. So if you kind of do those middle 3 points first with the proper concavity, it kind of helps you get the curve a little bit better. All right. So let's talk about reflections here a little bit. So as you guys know, tangent typically looks like this, right? And cotangent typically looks like this. But if we reflect these, in other words, if I multiply the outside by a negative, it's going to flip it upside down. Same thing over here with the cotangent. If I multiply that by a negative, it also gets flipped upside down. And so as you guys can see here, by putting a negative in front of the cotangent, it kind of makes it look like a tangent graph, doesn't it? And by putting a negative in front of the tangent, it kind of makes it look like a cotangent graph. Now, what won't change is the angles that we use. As you guys saw, that we use certain angles to graph tangent and a different set of angles to graph cotangent. But the shapes become identical if you reflect them. So I'm going to take the same instructions here that I gave you guys earlier, and notice nothing's changing except for this red part here that I'm adding. Okay, so for this red part, if we're graphing tangent or a negative cotangent, then it's right and up, left and down. But if we're graphing cotangent or negative tangent, then it's left and up, right and down. That's it. No big deal. So we'll do an example here together just for the heck of it. Let's see. Let's say I wanted to graph y equals tangent, negative tangent, x plus 1. Okay, so since we're dealing with tangent, middle angle is 0. We have 2 to the left, 2 to the right. We've got vertical asymptotes here and here. My midpoint is at 0, 1. Now we got to do the other 2 points. But that's where we look at this thing. Now when you have a negative tangent, it looks like a cotangent graph. Okay? In other words, it goes left and up, down and right. So I'm going to go, since you can imagine there being a 1 here, so that would mean I go left 1, up 1, left and right 1, down 1. So we're going to connect that dot to that with concave up, that dot to that dot with concave down, and stretch out the lines towards the asymptote. Okay, so when there's a negative in the front of a tangent, it looks like a cotangent graph, but notice that we still use the tangent angles. It just flips the direction of the graph. It doesn't change the angles, right? So you guys may feel like this is kind of overkill, but if you would like to try to practice graphing this really quick, go ahead and give it a shot, see what you get, pause the video. If you feel like it's too easy and you don't want the practice, then just go ahead and ignore this example and move on to the next. But go ahead and pause the video here, and when you unpause it, you'll see the answer. There you go. There's my angles I chose. I went ahead and used radians. Midpoint is at 0 pi over 2. It has a tangent direction because it's a negative cotangent. And we're going over 1 up 2 because of our stretch factor. Okay. And there you guys have it. Let's go ahead and move on to a whole new concept here. We're done graphing sine through tangent in the easy way. But what I mean by that is we've only been dealing with vertical transformations like shifting the graph up and down, or stretching the graph up and down, or reflecting the graph upwards and downwards. But now we're going to move on into horizontal transformations, and things get a little bit weird there. So today it won't be too bad, but we'll see. All right, so if you put a negative in here, that's going to reflect your graph. Okay, but it's going to reflect it differently. It's going to reflect it horizontally. So for instance, suppose that I gave you guys a graph that looked like this. Well, and I called that f of x. Well, f of negative x would reflect that across the y-axis, so it looks like that. Okay. Now, vertical reflections are where the negative's on the outside. That would make it look more like this, where it flips it upside down over the x-axis. But horizontal reflections reflect them horizontally. Okay, so we're about ready to kind of study what effect happens whenever you make the input negative on these functions here. For this, I'm going to come out a little bit. Now, let's suppose this is the graph of sine, right? We know that sine starts at 0, 0. You got to think back a few lessons now, and it goes up after that and then down. That's what sine usually looks like. But if I were to put a negative on the angle, it's going to reflect the graph horizontally. So it's like I'm going to take this shape here and I'm going to flip it horizontally. So here's what sine usually looks like, and if I flip it horizontally, now look at it. Now instead of starting at the midpoint and going up, it starts at the midpoint and goes down. Which, by the way, in case you didn't notice, that's the same thing that happens when you take sine and you put a negative on the outside. So let me reset the picture here a little bit. So right now, both of these are the same thing. They're identical. There's sine. And we already talked about what happens if you put a negative in here. It makes it go down instead of up. But what about if we put a negative on the outside? Well, that means we're flipping it vertically. So if I flip it this way, it actually turns out looking exactly the same as if you have the negative on the inside. Now, not all functions do that, but sine does. Functions that do that are called odd functions, but you don't need to know that right now, but there you have it. Now let's consider cosine though. Cosine. Now we learned about vertical reflection. So if I put a negative on the outside, that's going to take the cosine function, it's going to flip it upside down, right? And so usually cosine starts at 0 at the max, but now it'll start at 0 at the min, right? What happens if let me reset it here. What happens if we put a negative on the inside, on the x? If I do that, that's going to reflect it horizontally. And as you can see, it doesn't look different at all. They're identical. So putting a negative on the inside of cosine doesn't make it look like the same thing as putting a negative on the outside. Putting a negative on the inside just makes it look like there's no negative at all. They have the same outcome, and that's because cosine is symmetrical about this y-axis. So if you flip it, it doesn't look any different. Okay, functions like that are called even functions. Tangent. Now, we've already talked about what happens when you put a negative on the outside. That's where you would flip it upside down, and it makes it look like a cotangent graph, right? But Wrong button. But let's say I put the negative on the inside. What is that going to do? That's a horizontal reflection. It also makes it look like a cotangent. So whether you have a negative on the outside or inside, they look kind of the same anyway. Okay, so there's that. The same thing happens with cotangent. Okay, cotangent usually looks like this, but if I put a negative on the inside, it makes it look like that, a tangent function. The same thing happens if you put a negative on the outside. Here's what it usually looks like, but if I put a negative on the outside and I flip it upside down, it just looks like a tangent function also. So tangent and cotangent are both odd functions. Whether you have the negative inside or outside, it looks the same with either type of reflection. Cosine is an even function where if you have a negative on the inside, it doesn't look any different than the original function. So here's a summary then of what we've learned. Whether the negative is outside or inside for the sine function, you're going to start at the midline and go down. For cosine or cosine of negative x, you're going to start at the maximum. But if the negative is outside the cosine, you start at the minimum. Now, for these three functions, whether it's negative tangent or tangent of negative x or cotangent, they're all decreasing. Now, what do I mean by that? I mean that the graph goes like this. It goes down as we go left to right. It goes in that direction. Whereas if you have a tangent graph, that looks like a cotangent with a negative inside or outside, which is like that. Okay, so that's a nice summary of both vertical and horizontal reflections. So basically, it just determines where you start and where you go for each one of these. So that's a nice little summary to have. I don't think. So I think I'll just do one more example with you guys, and then I'm going to call it quits there on this particular lesson. I'll back up a little bit to a blank slide. Let's do the following. Sine of negative theta with a 2 there. Okay. So first of all, you guys got to remember what angles we used for sine and cosine. So you might need to flip your notes back a little bit, back when we did lesson 11.1. The angles we use for sine and cosine are 0, 90, 180, 270, and 360 if you're doing degrees. I'm not going to include the radians right now, but you could also do radians. The next thing we did was we plotted our k value, which is our midline. This one does not have a midline, it's 0. So my midline is actually just the x-axis. And this number is my amplitude, so I go up 2 and down 2. Okay. Now, we're going to graph the sine wave. Now, if you were to go back to this slide that I showed you guys a little earlier, right there, that summary slide, anytime you have a sine with a negative on the inside, you're going to start at the midline and go down. Okay, so I'm going to be starting at the midline, and I'm going to go down from there. And then we just follow the pattern after that. And there's my sine wave. And of course, as you guys know, we go ahead and just keep the pattern up after that. Okay, so that's it. So today when you're doing your homework, you have to look at what you have here. Is it a negative inside or is it a negative outside? You're going to use this little reference sheet over here to know where to start and go from there. Now, just to kind of make you think a little bit more, what if you have two negatives? A negative inside and a negative outside. Well, Let's just think about that for a second. Suppose that here's my, let's do a sine, we'll do the sine graph. So if I took this particular function here and I did a horizontal reflection, right? It starts at the midline and goes down. That's what would happen if you had a negative on the inside. But what happens if you have a negative on the outside also? So we've already flipped it horizontally, but now we also need to flip it vertically. It just resets it to where it was, so these double negatives cancel. But you kind of got to be careful. The same thing does not apply to cosine, because cosine is just a little bit different. We've already talked about how with cosine, putting a negative on the inside actually doesn't do anything to the graph. It keeps it looking pretty much the same. So if you had a negative inside and outside, since this negative doesn't really matter, you really only have one flip that matters, and that's the one that flips it upside down. So this is on this one, you would actually start at the minimum. Okay, so you can have doubles in that case, and there'll be like maybe one or two challenging questions like that on your to make you think a little bit, but that's pretty much the gist of it. So from there, I'm going to go ahead and let you guys work on your homework, and we'll move on to our next lesson after that.